I will dig deeper into processors, and some of you are curious how to speed up a processor. Okay, so we will discuss this right now in this set of discussion in next 20 minutes. Okay, so function of processor is to perform logical and arithmetic operations. Arithmetic, all of you know, right? And logic also all of you know. Arithmetic is multiplication is arithmetic operation, but logical is, in a program we have do some instruction, then if number is greater than 100, then do something else. So this is logic. So computer is not only computing. The calculator can do arithmetic operation, but it cannot do programming. So programming requires logical operations. Okay, and that CPU can do. And GPUs are not so good for logical operation. It can do some, but CPU is still more powerful than GPU. So I think I just want to make a remark now, but we will come back to it later. So CPU is full-fledged unit which can do logical as well as arithmetic operations. It can perform I/O as well. So getting data from the disk or sending data to printer. Printer is managed by CPU. Of course, there is some data sent to the cache, but CPU is the main driver of all stuff which is happening in a computer. Okay, and also in fact it's part of I/O input, interpret user commands. Okay. So like this one, or I am saying run this. Okay. So these are operations of a processor. So let us look at inside a CPU. So this is a sketch. CPU does not look like this, but it is a sketch. It is a good sketch. So we have arithmetic logic unit. Okay, it can do this operation ALU. Okay, so ALU is basically control circuits. So this is where all these operations take place. So addition required certain. Well, I don't know how to do this in a transistor, but addition will be some input to a transistor, something out will come. So basically zeros and ones. Okay, so 0 will come to 1 and 1 will come to 0. So when you add, you get an output which is combination of ones and zeros, and it says 1 plus 1 is 2. So 2 is basically 1 0. Okay, so carry over is 1. So it can be programmed, and it is programmed. If you look at the details in a book on computer architecture, you will find some of these details. Okay, they are registers. So you see, I mean, I want to operate on numbers, but I need the data to be sitting inside a plus b, right? So I want in my notebook I write a and b, then add. So the registers contain those numbers, and I put only 2 registers, but typically there will be 64 registers. So you can put 64 numbers in a given shot. So it turns out you can add 32 plus 32 numbers in given shot. Okay, something like that. So there are more registers inside a CPU. Program counter. So in fact there are reasons why this PC is there. So we go from line 1, line 2, line 3, but suddenly there is a jump. No? So if condition is there, so they will jump to some other program counter. So program counter is keeping track of which line of the code are you executing. ALU is here, apologies. ALU is part of control, is communicated. Control circuit and ALU are separate. So I think I made a mistake. ALU is sitting here and control circuit is here. It was below, so I didn't see that. Okay. So control circuit is basically, it is called control room. No, in a security or all this crime series, there is a control room which is managing this stuff. So ALU is a one officer who is doing all these operations of logical unit and so on. Now for you, one of the important things is called cache. So cache is where your data as well as instruction. So I have program which is 10,000 line code. I can't push 10,000 line code inside a CPU. So I will put maybe first 10 lines in a given time in the CPU. So this cache will contain this instructions. Well, 10 is too little, it can fit in around 1000 lines of code, depending on the cache size. And 1000 is good because whatever I need in next nanosecond or microsecond I have all the data on your desk. If you need some book, it's good to have it on your desk rather than going each time to yourself. So, cache is basically that you have something which is close to you and you can refer to it quickly. So, there is L1 instruction cache and L1 data cache. So, there are two different caches for that, okay, and they can hold quite a bit of, it's typically in kilobytes. Okay. So, I am going to show you some processors and typical cache, what is their size. Okay. So, this is L1 cache, but there is something called L2 cache and L3 cache. This is L2 cache and L3 cache. So, L1 is closest to you, but there is something slightly far away, is L2 cache, and even further is L3 cache. Okay. And L1 cache is the fastest, but L2 and L3 are slower, but not so slow. Okay. We will see the speed a bit later, but these are three hierarchy of caches, and they all sit inside the CPU. Memory typically sits outside, but there are now new chips where memory is inside the chip. I will not say inside the CPU, but inside the chip. Is it clear? So, this is how things are organized. Now, to make things faster, you want to push in more cache. So, you are not increasing the clock speed, but you have data which is close to you and you can do things faster. So, one of the thing is to increase more cache. Also, more registers, then I have more things we can do in one clock cycle. Okay. And there is a name for it, called vectorization. I am going to come to it in a minute. Okay. So, these are ways to speed up your number of operations in a CPU. So, this is the M1 chip of Apple. So, you can see we have CPU, we have GPU. This is single chip. Okay. RAM is sitting here, DRAM. Okay. Neural engine. So, this for image processing and cache. So, everything is pushed there in one place. Okay. So, this is definitely fast. In fact, it is also very efficient. So, Apple, if you have a laptop, battery lasts for something like 18 hours, and this one takes only 7 watts of power, or 20 watts of power max. Less power requirement is because of some more reasons, but clock speed is not pushed up. In fact, the CPU they divide into two parts. One is high precision CPU and one is fast CPU and a slow CPU. Okay. So, these are ways to make it more green as well as more efficient. It means faster in terms of number of operations. Please keep in mind, fast does not mean clock speed fast. Fast means how many operations can I do per second. Okay. That is what is the thing. So, power consumption is CPU. So, this is the formula, no? I mean, this is basically a set of resistors, I times V, I squared R. So, resistor is sitting basically in this. Well, this is not only resistor, it has capacitance and inductance, but this is the formula people use. So, V squared F. Of course, higher frequency will have higher power, no? Power is per unit time. But it turns out typically I used to think that these transistors have only 5 volt constant volt, but that is not true. If you increase frequency, then you need higher potential, higher voltage. Okay. So, more like if you are running, then you need a higher energy. Okay. So, V is kind of, okay, this is an approximate statement, but V is proportional to F. Okay. So, then what will happen to power is going to be F cube. So, that is what I said. This is like frequency doubling, it requires 8 times more power, which is not good. So, keep lower V and lower F, that is the idea. So, V is not 5 volt, but is 1 volt typically in a CPU, and frequency is around 1 to 4 gigahertz. There are people who try to bring down the frequency, like Apple is, for some CPUs it is lower clock. IBM, there was a machine which was running at less than a gigahertz, 600 megahertz. It is a very good machine called Blue Gene. Okay. So, you do not necessarily want to push up the clock. Okay. So, there is a statement by Moore, who this person is right here. So he had made forecast. This is 65, when I was not born. So this is that time. So the number of transistors in IC doubles every 2 years. Okay. So normally people want forecast, no? I mean, how will Indian economy be next 10 years, or how computer industry will be. So these ways, when people are thinking how we should how forecast, and people will take people will invest depending on the forecast. Okay. So he says, well, number of transistors will double every 2 years. Now let us see whether it is true or not. So this is I do not know whether you can see it clearly. Starts from 1970. It has 1000 transistors. Okay. So this is ICs now. Integrated circuits are already there. You can put 1000 in 70, but in this figure 2020 is the last, and it could put 50 million. That is the last one here. Okay. But I am going to show you some data now. In 2022, you can put 100 billion transistors in a chip. Okay. So that is what is 2022-23. So that is the stuff which is going on right now. So so packing more. I mean, that is so Moore's law is, in fact, this is line is roughly is following the double line. It's exponential growth. Okay, right? Year y squared. Well, y by y 0. So basically, it is exponential growth. So this is exponential. So that's why, I mean, you always, for most things you want to buy things now, but for computer you want to buy it later, because you will get a better machine next year with the same money. Now this is another, so this from the book, the Patterson and Hennessy. So this performance in terms of number of operations. So 1978 you can take as a 1 unit, and presently in 2012 it is 34,000 or 35,000 times faster. Okay. So this is 20 plus 20, well, around for 35 years there is a speed up of 35,000 in a single core. Okay. So that is a growth of computing power. So this is related to some of the questions which people asked. This is a nice slide, is taken from this website. So look at all of them. So this is number of transistors. So it is basically growing exponentially, which we saw in Moore's law. Moore's law holds, but it will not go forever. Because at some point you reach the quantum limit. I mean, I can't build a transistor with single atom. Okay. So presently the transistors are basically occupying size of 5 atoms. That is called 1 nanometer technology. Okay. So 5 atoms, that is the one transistor is taking that much space. Okay. Nanometer scale. So, but look at other numbers like clock speed is this one. Clock speed increased from 1 to 4 or 4 point, well, around 5, 6, but it has flattened. So people are not pushing clock speed. Then we have power. Power also, you don't want 1 kilowatt power for a CPU. It requires cooling and it's not green. So we are saturating at 200 watt, 300 watt, maximum 400 watt. Okay, nothing beyond. I mean, that will not be selling well. And another number is called instruction level parallelism. How many instructions can you execute per cycle? That was one of the questions. It turns out we can do up to something like here the number is 8, but you can put 16 in the new machines. You can do 16 floating point operations per clock cycle. Okay, this is called ILP, instruction level parallelism. Okay, okay, keep it 8. But the instruction level parallelism is more difficult than vectorization. Okay, so the thing is, we cannot pack more when we reach atomic or quantum limit. We are close to saturation, but doesn't mean that speed will go out. There are always clever ways to do it. Packing more transistor is not, well, of course it is quantum limit, but people always come with clever stuff. Okay, so even in classical computing, 2 nanometer technology, 50 billion transistors, each of size 5 atoms, and the size is fingernail. The CPU, the chip real which holds the transistor is of fingernail size, which is holding 50 billion transistors. And 1 nanometer is next, we do not have it yet, but 2 nanometer is already out. Okay, the other options are quantum computer, graphene based transistors, spintronics. Okay, so okay, now I am going to quickly look at this CISC versus RISC. Okay, so CISC is acronym for complex instruction set computer. Okay, and RISC is reduced instruction per set computer. Okay. Now this is basically how you do the operations. I want to add, or I want to do some operations, no, like fast Fourier transform. Okay, so let's look at CISC first. First thing came was CISC. Okay, so single instruction can execute several low level operations. Okay, so when you say go, so there are a set of things will happen inside a CPU. So go can we say, well, do fast Fourier transform of an array. Okay, as a complex operation, right? I mean, array could be size 16 numbers, or go could be add a and b, a plus b with 2 numbers. So second one is much simpler. But if your RAM size or if your cache size is less, or your RAM size is less, then would you like to do more, have more instructions or less instructions? Less instruction, right? So earlier cache size, RAM size was low. In fact, earlier machine, I don't remember now, it was RAM was megabytes. I had a 1994, I had a machine, PC, which is memory was megabytes. And megabytes means I want to, my program size should be less, because I can want to fit in the RAM. So since one instruction should do more things, right? I mean, that's what we want. So that's why complex instruction. So one instruction was more powerful, but required lot of integrated circuits which were very complicated, right? So in fact, there were math processor which can do one operation, one complex operation within a cycle. Understand? Multiply 8 set of numbers. Okay, A into B, but A was 8 numbers and B was 8 numbers, and one shot you should do it. So it's called math coprocessor, and people were designing that kind of thing because the RAM size was less. So loading the data from the memory register, arithmetic operations on the data, and second send back data to memory. So you are doing all these stuff, and arithmetic operation could be complex operation. So small size assembly code because RAM is less and less memory, and so Intel processor, which were one of the leaders in making this. IBM and Intel were early ones. Okay, Motorola I think came a bit later, and Apple is much later. Okay, Apple making chips. So now Apple is making chips, so which will cover it. Like M1 chip is Apple's chip. So Intel adopted the CISC strategy because RAM was less. But now RAM is not less, RAM is significantly higher. So people, this guy Patterson in Berkeley, they said, well, let's use simple instructions, so our hardware is not complicated, right? I mean, whether there are hardwares called FPGA, no? FPGA. These are like hardware you can program. It has RAM and it can do complex stuff. So instructions are simple, but so well, these guys said, well, let's make instructions simple. So our hardware is small or simple hardware, okay, and we'll have bigger data, bigger instruction sets or bigger machine code, but it's okay. Our RAM size is good, it's large. So they say, well, let's adopt this strategy. Hardware is simple and code blocks can be executed in single clock cycle. By the CISC, the operation need not be executed in single cycle. One operation is a well go, but it may take 5 cycles or 6 cycles. But we want things to be done in single cycle. So programming is simpler, your hardware is simple. So that's the idea. and so this RISC is what was proposed. It requires larger memory, it is faster. Well, I mean, writing code, writing compiler is much easier in RISC. Okay, and also it turns out it is less power hungry. Okay, so ARM processor of your all the mobile chips are ARM processors. Okay, so ARM are based on RISC, and M1 M2 chip. So one idea was this mobiles take less power. No, by design, if your mobile gets exhausts its battery in 1 hour, it is no good. So the people are pushing. In fact, Microsoft was tried first to make a laptop using ARM processor. In fact, they had a hardware, they had a laptop, but coding is, I mean, already we have a nice operating system, okay, some operating system. You need to change all of it to ARM. Okay, by the way, converting a sys code to RISC code is not easy. So they did not succeed, but Apple succeeded. Okay, so this laptop with ARM processor M1 M2 chip came first in Apple. So this in Apple, as I said, the power requirement is around 20 watts compared to 200 watt. Okay, that's why battery lasts longer. Okay, so ARM is one of the bigger candidates for supercomputing. Okay, there are machines which are supercomputers are built based on ARM processors. Okay, it is still fresh, but it's going to come. GPU is also one such design, but is different. ARM processor can do all things what CPU can do, or what Intel CPU can do, but GPU cannot do all what CPU can do. But it can be fast as well as less power hungry. Okay. Anyway, so this code I like. In fact, this is a nice code. Simple is beautiful. Okay, it works. I mean, this is an example where it has benefits. Also in physics, I think, or even engineering theory. So if your theory is simple, then you can think more. You know, is it correct or not? I find I can think in many directions if my idea is simple. It's too complex idea, then I can't navigate. Okay, so I think I will stop here, and I will do vectorization in the next class.